periodic table and calculators, close your Chromebooks. Also, get your study sheet out with the flow chart. You're going to want to follow along. And you know what? Go ahead and get a scratch piece of paper out too. Listen, the more you take notes on this, the more you write down the examples, the easier it'll be when we actually get to the problem. But without exaggeration, this assignment is probably the hardest assignment of the year. If it clicks for you and you know how to do it, good, congratulations. Even if it does, it's going to take you quite a while to complete these problems. Each problem itself is like multiple problems to do. So let's see what we have here. Let me get the PowerPoint pulled up, and we will get started on it. So today, what we're doing is we're going over the stuff that we kind of touched on last week. I don't remember exactly when I did this. I guess it would have been the review. The end of the review, before we took the test, I kind of talked to you about some bicycle parts and which would run out first. And that was me introducing what we're going through today. So, let me unfreeze this. Let me take a sip of my delicious tea.
Hey, what was the, hold on, what did you just say earlier? The study sheet.
You don't have a packet of the study sheet?
No.
And remind me if we have time after class or after I get done lecturing here, I can show you what notes to put on that.
All right.
So, and if you didn't take the test last week, make sure you get with me and during activity period sometime this week. It needs to be early this week to take that test. Pretty soon, I'm going to have to put grades in because we're getting near the end of the 6 weeks. It'll be next week. So I got to put grades in for that test. So if you haven't taken the test yet, get with me to take the test. What we're going over today, limiting reagents and percent yield. These are going to be two problems that take quite a bit of time to do and require you to go through all the steps. So it's important that you have that flow chart on the study sheet and that you're following through it and kind of understand how to use it. Because like I said, the problems, we're going to take the same problems that we've been doing. The biggest ones are like grams to grams, but we're about to double or triple them. And so every single problem is going to be at least twice as long now. What are we trying to do here? What's the point of this? We're going to start off with limiting reagents. So remember, the reagent is like your reactant. It's the thing that I put into my beaker to start the chemical reaction. Not the thing that comes out, that's a product. The reagents are the reactants. So when a chemical reaction is performed, the amounts of reactants used may not match the ratios needed to fully consume both reactions. So basically, if I take my two chemicals, and these are actually two different chemicals now, if I take these and mix them together to create a third chemical, most of the time, unless I plan for this to happen perfectly, most of the time, both chemicals won't just be completely gone. I will have something left over at the end, a little bit of one of these chemicals left over that didn't fully react. That's what we're trying to do with limiting reagents. I want to know which chemical ran out first, which one I have left over, and more importantly, how much I have left over. That's going to be important for like industrial, real life kind of job purposes. So one reactant is consumed before the other. Something's always going to run out first. What's going to run out is going to be the important part. I need to be able to figure that out. After one reactant is used up, the reaction stops, and that's important. If I need both of those chemicals to make my reaction happen, as soon as one of them runs out and it's done, I'm done with my reaction. In the same way, I need fuel and oxygen to burn a fire, right? I gotta have something to burn, and I gotta have oxygen to feed that fire. If at any point in time one of those things runs out, I either run out of fuel or I run out of oxygen, now my fire's done. My fire's gonna go out because there's no more reaction happening anymore. Same thing here. If I run out of a chemical, the reaction stops and no more products are made. So they go to the bicycle example. And I like the bicycle example because it's nice and visual and we can all kind of take something from it. So what do we have here? We have a formula, which I've written on the board over there. What does it take to build a bicycle? And we've written it out just like a chemical formula. I have 1 mole of frames, 1 mole of gears, 2 moles of wheels, and if I put all those together, I get 1 mole of bicycles out. And so each of these numbers is like my coefficient in my balanced chemical equation. Each of these things is like a chemical. So like a frame would be H2O. A gear would be CO2. Each of these is kind of like a chemical in a chemical reaction, and the numbers are like your coefficients. So if I have 4 frames, 6 tires, and 4 gears, how many bicycles can I make? Well, if I do each of these problems separately, if I just look at the gears, how many bicycles can I make with 4 gears? 4 bikes. If I look at the tires, how many bicycles can I make? Only 3. And if I look at the frames, how many can I make? 4. So I got 3 different answers, 4, 3, and 4. Which one's correct? How many bicycles did I actually make? 3. And so what did I run out of when I stopped at those 3 bicycles? I'm out of tires. So tires are my limiting reagent. They're the thing that I put in that ultimately I'll run out of, and that stops my reaction. That's my limit right there when I run out of tires. Now, these other 2, my frame and my gear, those are going to be called excess reagents. Because if I have excess, I have extra left over, right? So this is going to be my excess reagents. And I could do a little formula. Obviously, we can just see here, but you could write down a mathematical formula to tell you, oh, I will have 1 frame left over, and I will have 1 set of gears left over. And so that's kind of what we're going to do. We're going to do each of these equations and figure out our different answers. And then I'm going to take the lowest answer. Remember, that's the important part. We had 4 bikes, 3 bikes, and 4 bikes. The lowest answer is the one that gets built. 3 is my lowest answer here. So 3 bikes is actually what I end up building. That's what I'm looking for. So they talk about the limit and the excess. The limiting reagent is the one that's completely used up. So whatever I run out of and just completely disappears in the reaction, that's my limiting reagent. The excess reagent is the one I have left over. So the reactant that's left over in a chemical reaction is my excess reagent. If I plan it out perfectly and both of my reagents run out at the same time, like I measured perfectly to like the milligram beforehand, and I knew how much I needed, then maybe I won't have an excess reagent. Maybe they'll both be limiting. But most of the time, especially for sapling problems, you're going to have one of each of these. You're going to have something that runs out and something that's left over. Their example here, nitrogen plus hydrogen goes to ammonia. And so what they show you down here is that I have 4 nitrogens at the beginning and 6 hydrogens. When I put them together, what do I have left over? 2 extra sets of nitrogens, right? And so what did I run out of? Was it the nitrogen or the hydrogen that I ran out of while making ammonia? I ran out of the hydrogen. So the hydrogen would be my limiting reagent because it ran out. And when I ran out of hydrogen, I stopped making ammonia. Nitrogen is my excess reagent. I have extra nitrogen left over here at the end, just sitting around. If I'd done better at my job, if this were my job, I should have used less nitrogen, and I wouldn't have had this much left over at the beginning. I could have conserved some materials and saved my company some money. Identify the limiting reagent in order to accurately calculate the amount of product used. To determine the limiting reagent, you do your stoichiometry to find the amount of product in each reaction could have theoretically produced, and then you want the smallest number because you're going to get multiple answers. The smallest answer is the correct answer. The reactant that produces the least amount, the smallest answer, is the product is the limiting reagent, and that's where my reaction stops. Other reactants were excess reagents, and we'll see how we have to deal with those in just a second. Let's see. So step 1, I need that balanced equation. I need the coefficients. I need to know what's happening in my reaction. I need that balanced equation. Step 2, do all your stoichiometry. So step 2 is pretty long for just one step. They want you to do all your stoichiometry for all of your different reactions, all your different reagents, and get answers for all of them. And then step 3, ignore the higher value, only take the lower value. For the number of grams of the product, the number of grams of the product produced by the limiting reagent is the amount of the product that should actually form. So you want the lowest answer. That's going to be your final answer. So let's do an example. We got 3 different examples to go through, so I'm going to try to go through them kind of quick. But we need to do this to kind of set up how the problem's going to be. So I'm turning the lights on. Lights are coming on. Let's come over here and let's write out our example problem so everybody gets to see. So here's where you're going to start taking notes on your scratch paper if you got it. What are they? So same thing that we were doing for the test. What's my chemical A? Where do they start me out at? What's the number they give me to start out with? 10 grams. And do I have it for just one chemical or do I have it for 2? 2. So I have 2 starting points now. I have 2 chemical A's because I'm going to do 2 problems. They're both starting out at 10. It's easy when they both start out with the same number. It gets a little bit more difficult, not much, when they give you different numbers. But I have 10 grams of barium and 10 grams of sulfur S8, and they're going to react. What do they want from me? What do they want my answer to be in? Yes, they want the number of grams of barium sulfide. That's what they're asking me for. So they give me grams for my chemical A's, and they're asking me to go to grams for my chemical B, which is barium sulfide. That's what I need to do. So first thing I need is a balanced equation. I need barium and sulfur. So I have just barium, Ba, plus sulfur, which is S8. Oops. And then is equal to, it's going to go to barium sulfide, BaS, which I need to check this formula. Where's barium at and what kind of charge does it have from the periodic table?
On the right side.
It's a +2 because it's in the second column, right? Ba is in the second column, so it should be a +2. What's sulfur? What's charge is sulfur going to have? A -2, yeah, because it's in that same column as oxygen. It has 6 out of 8. It'll be a -2. So is +2 and -2 okay? Yes, so this is my actual formula. I don't need any subscripts or anything like that. It's just BaS. That's barium sulfide. Now, what's the last thing I need to do to this formula here? Yes, I need to balance it, right? It has to be balanced because I got too many sulfurs on the left side. I need more on the right side. So I put an 8 in front of BaS. Now I have my sulfurs balanced, but what do I need to do? I need to balance my barium. So I put an 8 in front of my bariums. Now, am I nice and balanced? Yes, so I'm good to go. I have my formula set up, and that's going to be the first thing they give me. Again, sapling will normally just give you the formula. So there it is. Now, I need to set up my problems. I know I have a starting number of 10 grams, 10.0 grams of Ba. And I know I have a starting number of 10.0 grams of S8, right? I got 2 starting numbers. I got 2 problems. How far am I going? What are they asking me for my barium sulfide? Grams. So this is a grams to grams problem. It's actually 2 grams to grams problems. So I look on my flow chart and I find grams of A and grams of B, and I see how far I need to go, right? So for each of these, I got to pass 3 conversion factors, don't I? I need the molar mass at the beginning, the mole ratio in the middle, and the molar mass at the end. So when I set this up, I'm going to do both problems all the way out to the end. So I'm going to have 3 different fractions for each of these problems. Multiply, multiply, multiply. And again, I hope you see, it's going to be important for you to write this stuff down and take notes. Just 1 grams to grams problem is already too long for you to do in your head. 2 grams to grams problem is going to be even worse. So make sure you write everything down and let's set it up. Now, the good news is if I'm doing the same problem, these are going to look somewhat similar. And the things that I have to do are going to be somewhat similar. So leaving grams and going to grams, what's this first thing got to be that I have to do? I use the molar mass. Am I dividing or multiplying? I'm going to divide by the molar mass of chemical A, right? And then what's the middle thing I have to do? The mole ratio, which is B over A. And then what's the last thing I have to do? Multiply by the molar mass of B. So you can see if I'm doing the same thing for both of these, they're going to be very similar. The only thing that's going to be different is my molar mass for chemical A, because they're different chemicals, and then my mole ratio. But I know what I need to do. Let's go ahead and set this up. Now, dividing by the molar mass A, what's my chemical A here? It's the barium, right? So what's the molar mass of a barium? What is it? 100 and what?
137.327.
0.327. And that's in grams. I'm dividing by it, so it's got to go on the bottom. And that's going to be equal to 1 mole of Ba. Ca. So now I want to do the same thing, but just different chemical. I'm dividing by my molar mass. I'm going to do the same thing for S8. So what's 1 sulfur times 8? Because I got to use my formula here. What's the weight of a sulfur times 8? 0.48 grams of S8. And this will be for 1 mole of S8. So now I've divided by my molar mass of chemical A. I'm done with my first part. Next, what I need my mole ratio. And what do I know about my mole ratio? It's B over A, and it's moles over moles. They're both moles on top and bottom. So I know it's got to be moles over moles on both of these. So I'll go ahead and pop that in there. And I know it's got to be B over A. My A chemicals are at the beginning. So I'm always starting with A, and I'm always ending with B. So my A chemicals are at the beginning. So I need barium, Ba, and sulfur, S8, on the bottom. What's my ending chemical for both of these? It's the BAS, the barium sulfide. So that's going to go on top of both of these, which is actually going to make things a little bit easier. BAS. And where do I get my numbers for my for my mole ratio? From the coefficients of the equation. So what's in front of BAS? It's an 8. So I put an 8 here. I put an 8 here. What's in front of barium? An 8. So this one's going to be 8 over 8. But what's in front of sulfur? 1. This one's going to be 8 over 1. So notice my mole ratio, or my molar masses are different at the beginning. And the bottom part of my mole ratio is different, but the top part is the same. They're both the same, BAS 8. So now I have my mole ratios done. What's the last thing I need to do for both of these? Multiply by the molar mass of chemical B. What is chemical B for both of these? The BAS. So what's a barium plus a sulfur? What's the weight of a barium plus a sulfur? It's going to be like 170 something? 160 something? 172?
169.33.
169.33 grams of BAS. Oh, wait. Yeah, I need to be multiplying. So instead of on the bottom, I need to put this on the top.
Nice catch.
169.33? Is that what you said? Cool. 33 grams of BAS over 1 mole. And then this is going to be the same because I have the same ending chemical, 169.33 grams of BAS over 1 mole. BAS. And now everything's set up. Now I've divided by my molar mass for both of these, used my mole ratio for both of these, and then multiplied by my final molar mass. So someone give me this top answer real quick, and someone give me this bottom answer real quick, and let's look at our 2 answers and figure out which one's right. Can you tell just by looking at this which one's going to be the limiting reagent or the excess reagent? Can you really? It's going to be kind of tough. Maybe if we had more time, we would take a survey and see who's right and who's not. So you got the bottom number? What's your bottom number?
Oh, I thought we were guessing.
No, you can guess, but I need the numbers so we
get the numbers right now.
can't just guess till the end. Anybody have the top or the bottom number?
52.82.
Is that the top or bottom? Bottom? 52.82? 52.82, and that's going to be grams of BAS.
Actually, I'm going to go with the top.
Anybody got the top?
Top.
Did you get it? Are you working on it?
Right?
Huh?
Whichever one's less or more, right? Less?
Well, let's get them first, and then we'll discuss it. Yeah. So what's the top one? What do you got? 98.64.
I got 12.
Yeah, but so there's no way that's right.
Yeah.
You got 12 for the top one? Or did you? All right, so we got 12.
No, so
12 point what?
3-3.
3-3? Okay, and if anybody got different numbers for these, let me know, because I don't know if they're right or not. Y'all are the first people to do it today. So, anybody want to double check the
I'll
bottom?
try.
No, I got it.
You got it right? You got it right? Okay, okay. I trust you. I trust you. So anyways, you get your final numbers here. Now, which one's going to be the correct one?
The limiting one's the top
The limiting one's the top one. So the only amount of BAS I actually made is this 12.33. When I got to 12.33, my barium, my 10 grams of barium is now gone. I've used all 10 grams of barium to make this 12.33 grams of BAS. This 52.82 never got made. The rest of that never got made. It stopped at 12.33. If I had more barium, then yes, maybe I get up to 52.82, but I didn't. I only had 10 grams of barium, so my equation stops here and nothing else is created. Now, did I use all of my sulfur? No, I didn't use all my sulfur. So now the next question is, what your boss is going to ask you, if you're getting a paycheck for this, is okay, I only made 12.33 grams of barium sulfide. How much sulfur did I waste? What should I have used as sulfur where I didn't have any extra left over? What kind of extra sulfur do I have? So that's another problem, which I'll show you in just a second. If you want to try to figure it out, you can go ahead and figure it out on your own. But we're going to go through this real quick. So let me bring my laptop back over here. Yeah, don't be wasting sulfur. It smells so wonderful. So let's see. They go through the same thing we did. Look, they set everything up the same way that we set it. They got their molar masses they're dividing by. They have their mole ratios. They're multiplying by the molar mass at the end. And they got, look, the same answers. We got 12.3 and 52.8. Just a little rounding differences, but the exact same answers. And we know now that the 12.3 is the correct answer. That's actually how much stuff we made. So now they go to the next question, which kind of builds off the same thing. Are they starting us with the same chemicals? Yes, but they're asking something different. When solid barium reacts with solid sulfur, S8, solid barium sulfide is synthesized. Calculate the number of grams of barium sulfide that will be produced when 10 grams of barium... What? No. That's what I already did. Oh, never mind. We just weren't done with the problem. I apologize. 12.3 grams, final answer. Now, we get to the next problem, which is finding the amount of excess reagent. So we already know sulfur is my excess reagent. I have extra sulfur left over. I used all of my barium up. It's done. Now the question becomes, how much sulfur do I have left over? I know it's less than 10 grams. It can't be more than 10 grams because I've already used some of it. So there's going to be some amount less than 10 grams, but what's it going to be? So step one, start with the amount of the product formed when all of the limiting reagent reacts. So how much product did we form when we actually did this reaction? What was our amount of product we made? Come on, we got the answer. Yes, the 12.33. This is my product. This is what I produced. And I have two different numbers here. One of them's the true amount. One of them's how much I could have made if I had extra material. So 12.33 is what I made out of my actual reaction. That's important. Oops. They're telling me to start with that amount. So I need that number to continue to go forward, and you're going to see why in a second. So subtract the amount of excess reagent used from the given amount of excess reagent is step 2. And then, they don't have a step 3. So step 1, what I need to do, I need to take this amount that I made in my last math equation and use the stoichiometry to determine how much I actually needed from that. And so this is actually where writing stuff down comes very much into play. And I want to show you this. Everybody look at this real quick, because this is actually kind of cool. It's not kind of cool. It's real cool. what we have here, I have two different problems. So I said, if I have 10 grams of barium and I'm reacting with sulfur, how much barium sulfide do I make? I make 12.33 grams. This math equation down here wasn't actually used. I mean, I had to use it to know which was the correct answer, but did I make 52.82 grams of barium sulfide? No. And did I use all 10 grams of sulfur? No. So I didn't really use this equation at all, but the question is, how much of this sulfur would I have used if I had actually stopped at 12.33 grams like the other problem tells us to? So what I'm going to do here, I'm going to take this as my new starting number, and I'm going to plug it in to this equation. And this is going to sound crazy, but you'll see in a second. This equation needs to be flipped, top and bottom, and left and right. And I will be able to reuse this without doing any extra work. What I'm going to show you real quick is how I would do it if I just had to do all the extra work. And then you'll see how I could have used this number. So I'm going to come over here and do it so I have plenty of room. What I need to do is start with my 12.33 grams of barium sulfide. So I'm going to start there. 12.33 grams of barium sulfide BAS. I'm going to put it over 1. And what do I want to know? What are they really asking me? They're asking me, here in my question, how many grams of sulfur remain after the reaction is complete? And so if you think about it now, I just have a different starting number. I'm going to start at the end with my barium sulfide. That's my starting number. I have 12.33 grams. And I want to go backwards and figure out how much sulfur I used to make that 12.33 grams. This is a gram to gram problem. That's just going backwards from barium sulfide to S8. So I need to have 3 conversion factors that I need to do. And just like those gram to gram problems, they're going to be the same 3 conversion factors. I need to divide by the molar mass for chemical A. I need to use my mole ratio. And I need to multiply by the molar mass for chemical B. So what's the molar mass for barium sulfide? We already looked it up, didn't we? Well, look on the board. Use your eyes and your brain. What's the molar mass for barium sulfide? But over there, did I multiply or divide by it? I multiplied, and it was at the end of the problem, right? Here, what am I doing with it? I'm dividing it, and it's at the beginning of the problem, right? So I flip it top to bottom, flip it left to right, and I end up with this 169.33 grams of barium sulfide on the bottom of 1 mole of barium sulfide. That should be a big S. Now, I need my mole ratio. What's my starting number? Or my starting chemical, BAS. BAS, and this is going to be in moles. What's my ending chemical? I'm going to sulfur, right? So S8 is my ending chemical, and this is in moles. What are my coefficients in front of BAS and S8? 8 for the BAS, and what's in front of the 8? Or S8, I mean? 1. So look, instead of 1 over 8, instead of 8 over 1, like I had on the bottom equation over there, I have 1 over 8. And then at the end, I'm multiplying by the molar mass for B. What's my chemical B? S8. What's the molar mass for S8? 256.48. Where there, I'm dividing it, and it's at the very beginning. Here, I'm multiplying it, and it's at the very end. So 256.48 grams of sulfur, S8, over 1 mole. And so before I do this, or before I have y'all do it, if someone wants to start on it, you can go ahead and start on it. Notice what I did here. Here, I'm dividing by this 169.3 at the beginning. Over there, I'm multiplying by the 163 at the end. Over here, I have 1 over 8 as my mole ratio in the middle. Over there, it's 8 over 1. Over here, I'm multiplying by 256 at the end. Over there, I'm dividing by at the beginning. So does everybody see how I kind of took this equation? I didn't get the answer out of this equation. So I take the answer out of the one I did, and I take the other equation and I flip it top to bottom and I flip it left to right, and that makes my new equation with my new starting number. Does everybody kind of see that? If you can see that and visualize it, it can save you a lot of time. That way, I don't really have to even set up that problem, or I don't have to think about it when I set it up. I just literally use the numbers that I've already gotten and make a new equation out of it. It's just flips top to bottom and flips left to right. Now it's created my new equation that I go through. And if I go back through this, someone give me the answer for this.
149.41.
What? That's too big. 149?
That's what I got.
What'd you get?
2.3.
2.3. That's going to be better. 2.3 grams of S8 sulfur. And this kind of makes sense. So now, what did they just ask? They asked, how many grams of sulfur remain after the reaction is complete? Think about it. What did I just tell them? I told them in order to make 12.33 grams of barium sulfide, I would need 2.3 grams of sulfur. So this is not how much I have left over. This is how much I used to make that 12.33 grams. How much did I start with in my sulfur? Yes, 10.0 grams. If I used 2.3, I'm just going to subtract. And my answer should be 7.7. 7.7 grams. And that kind of makes sense, doesn't it, right? Because if we look over here, just think about it in big terms. I started with 10 grams of barium, and I only made 12 grams, right, at the end. If I started with 10 grams of sulfur, I could have made 52 grams. Did I make even half of that? No. I made close to like a quarter of that. Not like half, but really closer to like a quarter of what I could have made. So when I find out how much of this I used, it's going to be down near around a quarter. That's what I came out to, 2.3, which is really close to 25%. And so when I subtract that out, I have most of my sulfur left over because I didn't really even use half of it. So I still have 7.7 grams of sulfur left over. I get the feeling this is going to be pretty confusing, but hopefully once you get this, it'll kind of click and everybody else keep working through it. So you can see they did the same thing we did. They got their problem set up. They set it up the exact same way that we did it on the board. These conversion factors are borrowed from that bottom equation there. Everything just gets flipped top to bottom and flipped left to right. And so we reused that, got our 2.33 grams that we used, and then we subtracted that from what we started off with, and now we have excess sulfur left over, 7.67 grams. And now, the final piece to this puzzle, theoretical yield and percent yield. This idea basically comes from the fact that, and I kind of mentioned this the other day, the lights are coming back on. If I put two chemicals in a beaker together and kind of mix them up, I don't want to bother go grabbing a beaker right now, but if I put two chemicals in a beaker together and I mix them up, even if I'm stirring, if you think about it like on the molecular level, individual atoms, so small we can't even see them, is there a chance that there's an atom of one of the chemicals floating around in here that just never touches an atom of the other chemical? They just never bump into each other. Yeah, there is. Even in a small school like this, y'all have people in your classes that you don't ever talk to. You don't ever meet with, you don't ever see after school, you've never played on a sports team with them. Other than this year, you've never been in a class with them. There's only 300 students in the school. It's easy to see everybody, but there's still people in the school that you don't know. That's kind of what we're talking about here. Even when I mix stuff up, even when I'm stirring it up for an hour, there's going to be atoms that don't combine and don't create my new chemical. And so that's the difference between our actual yield and theoretical yield. Theoretical is what I do on the board. If I take 10 grams of barium, how much barium sulfide can I make? What I'll find out is if I do this exact experiment in a lab with everybody, almost nobody's going to come out with 12.33 grams. Almost everybody's going to be below this unless you mess up somehow. And so what you make in reality is not the same as the amount you make on paper, and it's good to be able to do a little bit of math on that. And so percent yield follows this formula. If they show it in just a second, here it is. It's your actual yield divided by your theoretical yield times 100. And so it's just a quick little percent thing, us trying to figure out how much we made. They have an example here once we do the steps. There's only 2 steps. Step 1, find the actual yield. So step 1 is like do this entire problem over here and find out how much you actually did, which sometimes you've already done it and they already give it to you. Step 2, divide your actual yield by your theoretical yield and then multiply by 100. So they're always going to give you the actual yield. You're probably usually going to have to calculate the theoretical yield by doing a problem. Divide them and multiply by 100. So their example here is 18.0 grams of solid magnesium is burned in the presence of excess oxygen to produce solid magnesium oxide. If 27.3 grams of magnesium oxide was produced when this experiment was performed in the lab, what is the percent yield of this experiment? So this is my actual yield. And they're telling me this because I wouldn't know it unless I actually went into the lab and did it myself. And we're not doing that. So the thing that they give you is going to be your actual yield. I need to calculate my theoretical yield, what I would get on paper. And so I'm going to go ahead and do that. I'm not going to do it on the board because I want to save a little bit of time. But they're going to set it up the same way that we did it. We're starting with 18 grams. That's our chemical A. We're going to magnesium oxide. That's our chemical B. We set up a gram-to-gram problem just like we did over here. We divide by our molar mass. We use our mole ratio. And then we multiply by our molar mass for B. And we get the answer. Notice the theoretical answer is bigger than my actual yield. So what I could have gotten in a perfect world is 29.8 grams. What I really got in real life is 27.3 grams. Now, how good is that? How bad is that? I just do a little percentage to figure that out. So what I'm going to do, turn the lights on. I'm going to come over here, and I'm going to put my actual yield over my theoretical. So 27.3 divided by 29.8 times 100. What I get there? Somebody pop that in the calculator real quick. So this is basically telling me how good I am at my chemical mixing job. What is it? Somebody pop it in the calculator.
Come on, Adrian.
Y'all act like calculator work's gonna hurt you. It's practice. It's practice for real life.
I'm struggling with anyway.
Well, why don't you do a little bit of calculator work and it'll wake you up? Yeah,
No,
yeah.
it's
Let's
on.
keep going. Let's keep going.
tired.
Nah, you're going the wrong way. The wrong way.
91.61.
91.61. So, 91%. Is that pretty good?
Yes.
Yeah, we'll all take 91%. Your boss probably ain't going to yell at you too much for 91%. Now, if I only got 17 grams, now you're talking closer to 50, 60%, which in school is failing. You know it's going to be failing in real life job. So you're only getting 60% of what you should. And an actual factory job, they're probably going to have a talking to you. Maybe you get retrained. Maybe you get reassigned to a different place. You're up at 90%. Maybe you train the next new employee. And maybe if they have an opening for a management position, you get put in management. But that's what we're looking at here. That 91.6% is what we got. So that's good to tell us how well we're doing. And in fact, if we were doing labs and if I was like prepared for this, this is a common way that you'll get graded in your labs. They go in, they have you mix chemicals. They know based on how much you start off with, how much you should get at the end. And they basically see how well you can make that chemical. If I make 27.3 grams of it, well, you know what grade I got? I got a 92. If I only can make 17 grams of it, well, I'm probably going to get somewhere around a 55 or a 60. And so your ability to make the chemical directly affects your grade in the lab. That's a pretty common thing. So that's what we're looking at doing today. Let me open up the assignment, and it's just going to take you a while. So start on the problems. Make sure that you're working on them. When you have questions, let me know. But this is going to be a multi-day assignment. So you need to make sure you're working your way through it. You don't find yourself at test time being like, I don't know what's going on here. So we're gonna have multiple days.